In the final example in the previous video and also in the question below the previous video, we saw that when we took the triangular matrix and look at its determinant, we ended up with the product of the diagonal entries. This is not an accident. In fact, we have a theorem. I love me a theorem. If A is triangular, then the determinant of that matrix is the product of its diagonal entries. Just as we can use row reduction, use Gaussian elimination to find the inverse of a square matrix if it exists, we can use Gaussian elimination to determine the determinant of a matrix. We're going to need another theorem. Let A be a square matrix. If A has a row of zeros, then the determinant of A is 0. If B is obtained from A by interchanging two rows, then the determinant of B is minus the determinant of A. If A has two identical rows, then the determinant of A is also 0. If B is obtained from A by multiplying a row of A by k, then the determinant of B is k times the determinant of A. If A, B, C are identical in all rows except the ith row, and the ith row of C is the ith row of A plus the ith row of B, then the determinant of C is the determinant of A plus the determinant of B. If C is obtained from A by adding a multiple of one row to another, then the determinant of A is equal to the determinant of C. Finally, all of these letters, thingies, are the same with rows replaced by columns. Let's go through an example of how to use these to compute a determinant. Our first step is to do row reduction. But here we need to be very careful to keep track of each step in the row reduction. First thing I did is I divided the first row by 2, or I multiplied it by 1/2 to get this new matrix here. Then cleared everything under the 1 over here to get this matrix on the right. And then cleared everything under this leading entry here to get this final matrix here. Now, for the purposes of explanatory thingies, I'm going to actually name these matrices. I'm going to call this one, I'm going to call B, this one's going to be C, this one's D. Then, so by theorem 4.2, the determinant of D is equal to 1 times 2 times 4 times 5, which is 40. On the other hand, determinant of D is equal by theorem 4.3 part F to the determinant of C. That's because we did the operation of adding a multiple of one row to another. And the determinant of C, for the same reason, is by theorem 4.3 part F, the determinant of B. Then using theorem 4.3 part D, we get that the determinant of B is 1/2 times the determinant of A. So, therefore, combining both equations that we've just figured out, you see that the determinant of A is 2 times the determinant of D, which is 2 times 40, which is 80. Now let's look at this example. It's almost the same as the previous example, except I have a red 2 here in place of the 4 that was there before. Just as before, I can go and bring this into row echelon form, which for a square matrix will always be triangular. And now what I can do is use the theorems 4.2 and 4.3 to tell us, well, first of all, the determinant of this matrix here is equal to 1 times -2 times -2 times 5. And by theorem 4.3, the determinant of that matrix is also equal to, let's see, we have a -1 for the row 2 switching with row 3. We have a 1 for the middle thing here, because those are all taking a multiple of one row and adding it to another. And we have this 1/2 here, so we put a 1/2, and this is all going in front of the determinant of A. And so solving this for the determinant of A, we get that the determinant of A is equal to -40.